So it's going to be on surface area of revolution. The good thing is you don't have to do very many. Also, there's only one on your test. But that one, if you mess up any little part of it, it sort of is like arc length. It's got so many things built into the depth of solving it that you really have to be careful. So I'm not giving you a full-blown key today. I'm going to give you just the answers, and you're going to work for them on only 4 of them. So up here, I'm going to show you what loosely where the formula for it comes from. So right here, I have my graph of y equals f of x. So you can draw that in the top right. My screenshots that I took off the internet, like I said, the black background didn't work well with copying. It's just a ton of ink. So I'm going to also tell you that in reality, this was a piece of the function f of x equals x cubed, just so you know that. So it's on the xy axis. But really, when you're working with these revolving things, and even you're picturing them 3-dimensionally. So when we go 3-dimensional in math, we lay the x and the y axis, what I say, kind of down on the floor, and then we throw a third axis up through the middle that gives it its depth. Do you know what that axis is called? The z-axis gives it its depth. In Calc 3, you work a lot 3-dimensionally with x, y, z axis. You still are just going to be sketching yours on the x, y, and it's going to look like this. But technically, x is on the ground, y is on the ground, and d is the depth of it. All right? So this is me dropping it down on the floor digitally, and then allowing you to see some depth with the z-axis. So you're used to revolving those. So I took that piece of my f of x equals x cubed, and I revolved it right here around the x-axis, and it makes that shape right there, kind of like a funnel. If you want to try to draw that, I think I'm going to pause. Are some of you trying to draw it? Good, I see that, and you should, because it really helps you get an idea. I'm just such a horrible sketcher. I've gotten way better over the years, so I do attempt to draw them for you when I can. But I am not the best at sketching. So I'm going to pause that and let you guys sketch that out. Or I'm actually just going to kind of keep talking through it. You're used to revolving and finding the volume or the amount of space inside of that funnel. We've also done the arc length, which would just be how long this little red piece is. That's what we just finished. All of the formulas that you use in calculus have sort of a similar background to them. You're adding up how many things? An infinite amount, right? As something gets smaller and smaller and smaller and smaller, correct? So the formula for this one actually makes more sense, I think, than the arc length formula. Because what you do is you go on your function right here. So there's my function, y equals x cubed. I'm revolving it, and I want to find the surface area of revolution. So, like if I were to paint the outside of the funnel, how much paint I would need. I'm going to bring this down a little bit so, oh yeah, that was nice. Where did it go? Uh-oh. Just a second. I lost it. There it is. Okay, so anyway, when I go to this bottom left, I took the 3-dimensional piece away, but do you see these little, like, strips inside of here that look kind of like ribbons? Here's one of what I would call one of the ribbons making the surface area. Does that make sense? So if I were to cut this ribbon and lay it flat and do its area, that would give me the surface area of one of the infinite strips. So you're picturing like ribbons, does that make sense? Wrapping around. However, I made a finite one, and it looks like it's a little offset here, and it is. But on this ribbon, if I were to lay it flat, what would the length of it be? Picture me cutting it, laying it flat. What would the length of it be? You could be doing this. The what? Circumference. So it's going to make sense to you that there is a 2 pi out front. And it's 2 pi. And how do you get circumference? radius, correct? 2 pi r. Now, if, this is important, if you're revolving around the x-axis, like my picture is, then your radius is from here to here. And it's on the function, and it's just the f of x. Don't you agree with me? It's how pi this is as I travel along the curve. If I did it right here, my radius would be the height on the curve. Does that make sense? So I'm going to write this as 2 pi r, but then I'm going to fix it. And then its depth, I'm going to have to go with a different color so you can see it. And I think I'll go lime green. I'll really make it stand out. Right here along the curve is kind of what's making one of those ribbons. It's a little tiny piece of the arc length. Don't you agree? Right? So it's a little tiny piece of the arc length and then the circumference of the circle. And you might say, yeah, but that arc length is giving it some slant. As they get closer and closer and closer and closer and closer and closer together, they won't. Does that make sense? So the formula becomes 2 pi r, which would be the length of the entire ribbon, times its little teeny bit of depth, which is a piece of the arc length, which is why we had to do arc length first, right? So in loose terms, we're memorizing the formula, and it works. Like usually sometimes in May, I'll say, do you guys remember the formula for surge breaks there? And I go, 2 pi r arc length, because you sound like a pirate. Right? So it's easy to remember, 2 pi r arc length. But now we have to tweak it. But do you get where the formula is going to come from? This is going to be the length of the ribbon. This is going to be its little teeny piece of depth when I revolve it around. Good so far? So what's going to happen is, and I'm only going to do, I think, 2 examples, and then I'm going to derive something from our geometry. So it's 2 pi, but how many of those little strips am I going to add up? An infinite amount. As the limit of their depth or the arc length goes to 0, that's the definition of our definite interval. So we're going to throw that right there. Our arc length is a formula. The square root of 1 plus what? dy dx, what do I do with it? Squared. And we're only going to do, these actually are just as easy, dx, dy as dy dx, so it doesn't really matter. So then we have to talk about what that radius is. I told you when I revolve around this x-axis right here, my radius of this circular strip would be the height on the curve. It would be f as a function of x. So in this particular case, my radius would be x cubed. Do you agree with me? The distance from the axis to my curve would be the height on the curve. So then you just use the function. Are we good with that? If I revolve, though, about the y-axis, and just watch this, then I would be taking it this way, and my radius wouldn't be f of x. It would be what? X. Okay? So you have to decide, if you're revolving this way, your radius is the height, which is f of x. If you're revolving this way, the radius of your little strip becomes x. Are we good? It's harder when it's f of x because it's more beefed up. So we're going to go 2 pi f of x if we go about the x-axis. Then we need the y value for the height or the radius of a strip. Or it's going to be 2 pi, and you're going to integrate. We're always just going to integrate, though, left to right. So that's how these are generally done. X, and then still a little piece of the arc length, and then a dx. All right? So, and this would be if we're going about the y-axis. So you have to read carefully. Most of them go about the x. I think there's one on your homework I have to go about the y. On your test, I have you go about the x. All right? So that's kind of what you need to be most proficient at because that's actually the most applicable. So we're going to go take our example right there of this actual problem and figure out the surface area of that funnel-y looking thing. So here's how it works. We're going to write it down. My function is f of x equals, and put it in that workspace. And I think it's, did I say from 0 to 1? I lost my problem. I did. Here, thank you. And we're going to find its surface area from 0 to 1. So the first thing I'm going to do is write surface area equals. There's a 2 pi. It's easy to remember. 2 pi r arc length. We're going to integrate from 0 to 1. We're always just going to integrate. We're going to do all the x's. Then we are going to have our radius, which is our function, times the arc length, which would be 1 plus. And now I need to take dy dx, and I need to square it. So what's dy dx, or f prime of x? Go ahead real quick. 3x squared. In AB right now, they're doing that the long way. They're in 3x, what, right, Caitlin? Isn't that 3x squared the long way? But I told them in a couple days you're going to just tell me what the answer is. I need to square it, so what am I going to put in my radicand here? 9x to the 4th dx. Now I'm done with actually the model for surface area. The rest of it is how you tackle the integration, and there's many ways. This one perfectly lends itself towards what? This is U sub, and that's usually, I've always told you, U sub is king on the application. So let's go over here on the side, and who's my U? You got it, inner function. So again, these problems are so powerful because you're learning pretty powerful formulas. You're going into 3 space, right? You're also doing derivatives and integrals within the same problem. And then they're all have twists to them. So if my u is 1 plus 9x squared, my du dx is 36x cubed. I like that. Remember why? It's a multiple of what I need it to be. So what am I going to throw immediately right out front here of my integral? 1/36. Perfect. And then that means I'm left with the square root of u du. What is wrong with mine? It's a very common mistake. Yeah, do you see it, Kevin?
You can change
the limits. I have a function of u, a differential of u, and my limits are still for x. Watch that, right? Because with u sub you have to be careful. So let's go change our limits. What would my new limits be from? 1 to 10. Alright? So I will go from 1 to 10. And then it's just our normal integration. So we've got the pi 18ths hanging out front. I would have u to the 1/2, and I add 1. So I'm u to the 3/2, right? U to the 3/2 with a what in front of it? 2/3. Then that's what? Pi 12ths? U to the 3/2, am I good? Right? Wait. No. Cancel pi 18ths.
Yeah.
Right? Equals pi 18ths, and that would be my u to the 3/2, and I changed my limits as Tyler told me to, so I go from 1 up to 10. How are we doing so far? Good? What did I do wrong? 2/27. You are right. Wait a minute. 1/27. There we go. Arithmetic sucks. All right. So then this would be one where you think you're going to get your answer as a decimal, or are you going to be able to simplify it, or is it going to be left pretty ugly? And how you answer yourself is, do I have a calculator? No. If I did, I would have done Math 9 way up above, correct? Do I know the square root of 10? No. So it's just going to be an ugly looking answer. Does that make sense? If this was a 9 up here, then it'll be a nice pretty answer. So they get ugly. We're going to go over here, and it looks like we would have pi 27ths, and then in parentheses, I would have 10 to the 3/2, or the square root of 10 cubed, which I don't know, so I'm just going to leave it. 10 to the 3/2. Then what? Minus 1. Okay. If the answer that I give you is more simplified, you just simplify it more, but I don't think that gets really any better, and so I'm done with it. So it's a new formula, but it actually makes a lot of sense. But the integration can get messy. So I've got 2 I'm going to do with you again. So it doesn't say arc length, it says surface area, but we have to know arc length to do it. So it just adds a whole other layer. See if you have the formula memorized. If I show you where they come from, I think it's more likely that you would remember it. Did I make a mistake? No? Oh, Graham? That's okay. He's special.
Oh my gosh.
And I just said that for the whole world to hear.
Yeah, you should not.
Oh, sorry about that. Alright, so see if, just by visualizing, if you can write what you think the formula is. Keep in mind, sometimes it helps with that sketch to figure out what's going on. So 3 word X is kind of like this. I am going to take this shape right here. Oops, I didn't give you limits. Let's go 0 to 4. 0's nice. I'm going to take that and revolve it this way. And I'm going to find the surface area. So you have to be a little bit careful because on this one I said about, oh, that one does say about the x-axis. I love it. About the x, oh, damn it, why does it keep doing that? There we go. Nope. There we go. So we are going about the x-axis. So we're going to take these little strips. They have kind of those little hypoteni from the arc length, right? We're going to spin them around. So see if you've got it down. What am I going to write down first for my formula? Not because I have to look, but I kind of get where it's coming from. 2 pi times the radius. The radius on this one is going up, correct? So I am going to use the height. So in my integral is a 3 root x. Agreed? Do you remember what else? That's the circumference of one of the ribbons. Now I need its little tiny piece of depth. Yes, it's at a slant, but when there's an infinite amount, it starts to flatten, right? So what do I use for the depth of it? Arc length. 1 plus my derivative squared, which I'm going to go calculate off on the side. All right, now I've got it set up. I told you we were going to go from 0 to 4. I forgot to put the limits on it. I just typed this like on the fly. I needed new notes. All right, so let's get the 3 out front while I'm at it. Bringing your constants out front with these because they get so messy is super helpful. All right, looks like I still have my root x in there, which is making me a little concerned, but we'll see what happens. So then I need to take the derivative of what? 3 root x, right? So over off to the side, I've got my function being 3 times the square root of x. I'm just going to call it y prime instead of dy dx, right? What's its derivative? If you screw that up, the whole problem's going to be a mess. So what's the derivative of 3 root x? 3 over 2 root x. We've had that one so much, right? What do I need to do with the derivative? I need to do what with it? Square it. So I have my derivative squared would be 9 over 4x. Right? You good with that? Am I going too fast? Too slow? Just right? Just right? All right. So this would be 9 over 4x dx. Now everybody watch, because this right here, what happens like with your algebraic manipulation, sometimes is where these fall apart. It's not the calculus. The calculus is layered, but they're kind of simple layers. That is an easy derivative, don't you think? Just had to square it. All right, so my only problem right now is this integrand is quite a disaster. So we've been talking in AB quite a bit about getting singular fractions for these. Crisscross what? Multiply across. It's a very big cleanup technique when you're working with fractions and complex fractions. So watch what happens. Kind of have that in your brain that you're going to need to. I'm going to put this as something over itself. And I'm going to write it as a single fraction. What would that fraction be? It's not hard. It's a quick one, right? 4x plus 9 over 4x. All right. Now watch what happens with this guy. Okay? I'm going to scroll a little bit because I'm going to slow up right here. There's a part of this that you can pull out front. There is a constant in there. Where is it? Where's your constant that can come out front? This is a product. What do you think I can pull out front? What do you think, Owen? So I'm going to pull something out of there and get it out front. The square root of what? This one?
Well, you can
That's
square root
it. That one. Point at it.
because it's
I can think of those separately as root 4. And if you want to, actually, I might not because this is my first one. I think I'm not going to skip the manipulation step because I remember on last year's test, this step, it's a different problem, but a similar little move here is what they couldn't get past, and then they had to leave it blank. All right, so I'm going to split that. You are totally allowed to split up roots like that. We know that, right? So now when I ask you, where's the constant? You can't do pieces of a sum. That's totally illegal. That would be like you telling me that this is 8. You can't do them separately. So the top, illegal. But what can I do on the bottom here? What's root 4? 2. That's what I can pull out front. I'm just going to let that settle because I'm not doing very many of these. Do you see why I can do that? This right here is the square root of 4, which is really what? 2. Now watch why that's nice. What do you now see? I kept canceling that. I probably wouldn't have seen if I didn't do that. Does that make sense? So this 2 is going to come out front, and I'm going to do a rewrite, and I'm going to get rid of my chicken scratch over here. All right, so I've got the 2 coming out front. That's going to make a 3 pi. I'm still going from 0 to 4. There hasn't been any use of that's happened yet or anything. And then the root x's cancel. I don't know if you want to use a different color to show yourself that those are canceling, because this is something you're going to want to do to study for that test on our extra day, because Friday is going to be to go and look at these examples again. So once those cancel, I'm left with the square root of 4x plus 9 only in the integram. I could have given that on the first day of USUP, correct? Because who's u? 4x plus 9. Who's du? 4. And I can get rid of it, right? With a what? Fraction correction. Of what, Jacob? 1/4. If you don't need to write that down, don't. If you need to, write it down. I think most of us are at the point where you're like, all right, that's my, you might want to write it down just to change your limits. It's 4x plus 9, right? My limits would now be from where to where? 9 to 25. I'm liking that. Square root goes pretty nice, right? So I now have a root u, a du, but it's a 1/4 du. So I'm over here, and my new limits. How'd I do? You're nodding, Alexa. Does it make sense? It's a very in-depth problem. Lots of layers to it. But every layer you guys have been very good at separately. So it's kind of like you're just mixing all this stuff together. All right, so let's go over to this guy. 3 pi over 4 is still hanging out front. Do you see why I can only put one of these on the test? I have to, otherwise I don't have time to test you on ArcLink and to test you on multiple choice and to give you an FRP. So I got to test you on everything, so there's a little bit of everything. So you got to make sure you have those little pieces correct. Anyway, so this would also be my u to the 3/2 and my 2/3, and I'm going from 9 to 25. Now, Doug, do you know the square root of 25?
5.
And the square root of 9?
3.
That means this is probably going to be a nicer looking answer than the last one, which is a fluke because I made those limits up off the top of my head, actually. I just threw them up there. I was like, oh, sweet, those are nice choices because I'd forgotten to put them on there. So I think, do you guys need work on the arithmetic of this? Because I would like to get you to your worksheet. Okay? So I'm going to leave that, but you put the, obviously you cancel these, you have pi halves, and then you have 25 to the 3/2 minus 9 to the 3/2, both of which are nice. All right, next up, I'm going to tell you we're going to do this one on the interval from -2 to 2. And there's a reason I chose this particular function. All right? I'm going about the x-axis. So we're going to start. Here we go. 2 pi integral from -2 to 2. Could I go from 0 to 2 and double? Yes, if you know that that's symmetrical, which you should. Do you guys know what this is the graph of? Square both sides. You get y squared equals 4 minus x squared. Move them, and you have x squared plus y squared equals 4. What is that? That's a half of a circle with a radius of what? 2. Right? So if I go from 0 to 2, I'm fine. So I'm going to do that because I love when I'm doing stuff by hand. You see why I would like to do that? I'm going to avoid some mess when I integrate. So, what's my formula say? It says I'm revolving about the x-axis, so my radius would be up, it'd be a y value. So a good way to remember it is, about the x-axis, the radius is the y value. About the y value, the radius is what? X. They don't mesh. Alright. Then I need that guy's derivative. That's a good one. Take the derivative. Now I'm doing the chain rule. And I did U-sub. And I did arc line. And I have to know the graphs. Don't be scared away, Caitlin. It's not that hard. Right, guys? Alright. Go take that guy's derivative. Don't forget it's the chain rule. What's the outer length of the chain? 1/2. Yeah, I heard it. What do we do with the power? Let's review the chain rule real quick, right? It comes out front. We knock it down 1. But then what do I also need to multiply by? The what? The guts. And what would the derivative of the guts be? Negative 2x. Perfect. Before I square it, I'm going to give it a bath here. Alright? So I'm going to take the 2 off and the 2 off. And I'm going to throw, what do I have, a negative x? I'm going to throw my root down in the basement. There. That is my very clean derivative. And I have a linkage error. I'm going to fix it right now. You ready? Alright. So, what am I supposed to do with the derivative? There's so much to do. Luckily, your assignment's only 4 problems. It's nice. It happens in here a lot. There's not many to do. But you need to have your proof in a group on each one. Right? So what do I do with my derivative? Square it. Okay? And then I add 1 to it. So I have to do 1 plus. I have to square this derivative, which would become x squared, negative x times negative x, over 4 minus x squared. I'm going to tell you, because I've taught this class for many years, that usually goes very well. It's the issue of the mess in here. So what did I tell you to work with first? The what part of it? This first part of the root right here, or this second part? The second part. And what did I tell you to do? Get it as a single fraction, because usually things will clean up. So, not always, but it never does any harm, and it often does a lot of good. Alright? So this guy, I'm just going to let hang out front and hope it cancels. Do you think it will? Actually, probably, because it's ugly. Right? So I'm going to hope that cancels. And then under my big arc length formula, I'm going to crisscross applesauce. So I'm going to have 4 minus x squared on the criss, plus x squared on the cross, all over, multiply across. I love it. This is beautiful. Are you nodding? I'm waiting to see that, like LP, you're nodding, correct? This is lovely, because gone, gone. If I broke up the root of this quotient, what also is going to go? The top and the bottom, and what's the square root of 4?
2.
That whole thing, when I took that method of cleaning up in there, is a 2. That's pretty sweet. I want to make sure you're watching, though. How did I end up with a 4 out front instead of a 2? It was 2 cut. I did. I only went halfway, and I'm doubling it. All right, so what's the antiderivative of 2, twice x, from 0 to 2? What's my answer? Okay, now watch. I'm just going to show you something. 16 pi. That was an awful long route to what my geometry students will be able to do like this. Because they're going to be told the surface area of a circle. Do you guys remember the formula for surface area of a circle? Some of you might. You don't know where it came from, so you forgot it. In geometry, you got to write it on a note card. There's a formula. Guess what's in it? Does anyone know? 4 pi r squared. So we got somebody who remembers it. And what's the radius of my circle equation that I gave you? It was 2, correct? They'd just be plugging in at 2. Who knows more? No.
We
They're given a formula where they have no idea why, and they just, oh, the radius is 2, I plug it in. So at the very bottom of your worksheet there, where does that formula come from? It comes from this process. So I've been kind of putting that in every once in a while. John said it was 4 pi r squared. He does not know why. Right? I try to tell my students, so I'm like, it takes 4 circles to cover the sphere. But that's just like a fact. It's not a proof. So here's what we're going to do. We're going to hop on here. And we're going to put any circle of radius r on our paper. Okay? Historically, this is where the geometry kids get to use that formula. This is where it comes from. All right? It's a great problem. So and since you're listening so well, I think I'm fine getting your homework on. What am I doing tomorrow? I'm fine with it tomorrow because you'll finish in class tomorrow, and then if you want to, because everyone's focused. I'm fine with that, okay? Tomorrow is practicing 4 FRQs. It's going to take you 45 minutes to finish in class. So consider today's homework for the next 2. Good enough? All right. So we're going to pretend we're revolving this around, and it's going to make a basketball. We're going to find the surface area of the ball. Make sense? Yes. And this is for a circle of any radius r. Agreed? And we're going to revolve it around the x-axis. So I'm going to take one of those ribbons. They aren't rectangular slices. You're actually working with like a ribbon around the ball. All right? And what I'm going to do is say, well, how high is this? When I put in x, what is the height? Well, x squared plus y squared equals r squared from Algebra 2, the standard form equation of the circle. Agreed? I'm going to solve it for y, and I'm going to get the square root of r squared minus x squared. That's right here for a circle of any radius. That's any point on it if I were to plop it on the coordinate plane. Are we good, old man? Okay. So when I go and do my formula, 2 pi from, I'm going to go 0 to r. I'm only going to do a quarter of it and get half of the surface area. So I'm going to go from 0 to r. So what else am I going to do? I'm going to take care of that right there. So that's going to give me the whole thing, even though I'm only going to focus over here in the first quadrant. I don't like negatives. I'm avoiding them. Circles are symmetrical, so I'm golden. Correct? Now, this radius, I'm revolving it around the x-axis, is the y value, or the height. Oops, I forgot my square root. Did I erase it, or did I actually forget it? Oh, I wrote it down. All right, so the height would be square root r squared minus x squared. Then I need that little piece of arc length. All right, let's go do it. It'll be the square root of 1 plus, gotta go do it. You guys go do it. Go do your dy dx. Here's your y. And again, r has to stay in here because this formula has to work for any value of r. All right? Oops, a little bit. So we're going to take that derivative. What rule are you going to use? Chain rule. Your derivative should have been, if you're done with it and you cleaned it, a negative x over the square root of r squared minus x squared. Is that correct? Was that your derivative? Did I do it wrong? No. It'd be 1/2 r squared minus x squared to the negative 1/2 times what? Negative 2x. X is the variable, not r. What does r stand for in this problem? The radius of any circle, which when we plug it in will be a number. Right? So negative x is correct, because the 2's cancel. I was right. Pretty faces. Oops, I'm recording. There it is. Right. So, what do I need to do with my derivative? Square it and put it under here. Negative x times negative x is x squared. The square root of is r squared minus x squared. And I'm not going to freak out because I have all these variables. I'm going to do what I did on the other 2. What part did I deal with under the 1 plus? Make it one fraction, exactly. So the 4 pi is out front because I had a 2 and I'm using symmetry to double. This guy I'm hoping is going to cancel. Do you think it will?
Yeah.
Well, yeah. Somehow my answer's got to be 4 pi r squared. Stuff's got to blow up, right? I've got a mess here. So when I go under here and I put a little 1 under there, I get r squared minus x squared plus x squared, crisscross, all over, multiply across. It looks horrible, but in my mind I'm going, sweet. Are you? I see some of you like, oh, yeah. In my mind I'm like, this is super ugly. Historically, how the heck did they come up with 4 pi r squared for the surface area of any sphere in the world at any time of any day in any place on Earth? Right? This thing cleans up. Because what's this guy here? Gone, gone. If I made these separate, gone, gone. And what's the square root of r squared? R. So this would be 4 pi from 0 to r of r. This is where you have to be careful. R is not going to become r squared over 2. Correct? And you're shaking your head, Joel. What's the antiderivative of 5? Mod x. R is a constant. It stands for the radius of any sphere. So this would be 4 pi, what? Rx. That I'm integrating as x goes from 0 to r. What do I get? 4 pi r squared. That's where the formula comes from that I just tell my geometry kids. And it's so easy for them because I tell them, find the surface area when the radius is 3. And they go 4 pi 3 squared. But you don't get the significance of it. Like where that stuff comes from, that's cool. I think. Alright, I'm going to give you the homework. I accidentally didn't get it back to back, so it's 4 problems, but it has a staple because I forgot to circle one side of the page. So there's dead space. I have to give you a couple. No, I don't. I didn't only give you 1 minute. Only Caleb has to do it because the rest can just do that.
Appreciate it.
Is anyone even gone today? I probably didn't get on. Well, then I have it for 2. Yeah.
No one cares about Hannah.